here, and we are very fortunate to have today distinguished analyst, Marta Lewicka, who works on many areas of analysis, but in particular, counting variations, partial differentiation, and the systems and much more. I'd like to do a brief introduction to highlight her career. So she obtained her PhD in 2000 as the CETA. I don't know exactly what it stands for in the design along this way, but everybody knows about CETA. And then she followed her PhD by two prestigious postdoctoral positions at Max Planck Institute and at University of Chicago. She then moved to the States after the University of Chicago, very to the States. But after that, she took several positions as a faculty, and one of them as doctors. And in the end, in 2011, she switched to the University of Pittsburgh. She has been awarded several recognitions for her work, many lectures, but also the fellow of the American Mathematical Society and the vice president, vice chair of the group in analysis of factor differential equations, and a fellow of CSMQ. So we are very happy to have her today, and we'll talk on Convex integration for Monge-Ampere.
Thank you for this generous introduction, and I would like to especially thank Rustom and Jessica for the very kind invitation. And I also would like to recognize the Simons Foundation who facilitated my visit. So I'm on sabbatical, so I'm going to stay a month and a half in Montreal. So I hope to continue, discussions and friendship and collaboration with those of you whom I know, and make more friends and more collaborators during my visit. So I'm going to discuss my recent line of results, which is here encapsulated in this title, Convex integration for the Monge-Ampere system. So what is Monge-Ampere system? Let me explain that first. So basically, just in one sentence, the Monge-Ampere system is a generalization of the Monge-Ampere equation in its proper geometrical context, where Monge-Ampere equation arises as the equation for prescribing the Gaussian curvature of a two-dimensional surface embedded in 3 dimensions. Okay, so without further ado, here is the introduction of the Monge-Ampere system. So since this is a colloquium, I'm going to hopefully speak in a very, in a way that should be understandable to all of you. If anybody has a question, please do not hesitate, asking for a further clarification. So think of a scalar function v posed on a two-dimensional domain. Okay, so omega here is two-dimensional. So then the Gaussian curvature of the surface, this is the surface described as the graph of v. So v is this vertical displacement on top of the two-dimensional domain omega, is given by the formula that's familiar to all students, you also. Namely, it's determinant Hessian of V. V here is a 2x2 matrix divided by basically 1 plus, gradient V square. So if instead of V, I think of epsilon V, where epsilon is a small parameter, ultimately converging to 0, then the formula becomes epsilon squared determinant Hessian V divided by 1 plus epsilon squared gradient V square. So this denominator is basically 1, whereas the numerator is of the order epsilon squared. So in the asymptotic expansion, the prevailing term, the first order, leading order term, is epsilon squared determinant Hessian V. So equating this determinant Hessian V to a given prescribed scalar function f, on omega, reflects the prescription of the Gaussian curvature of a shallow surface. So this is the point of view where I'm departing from. So now imagine you want to do the same for a d-dimensional surface, where d is an arbitrary number, embedded in a d plus k dimensional ambient space. So in this first half of the slide, d is 2 and k is 1. So I have a 2-dimensional surface in a 3-dimensional ambient space. So now v goes from d-dimensional domain to k-dimensional to Rk. And now I'm going to think about of the metric, that's the pullback of the Euclidean metric via this deformation, which reflects the epsilon v displacement in the k dimensions out of this d-dimensional set. Okay, so it's very easy to compute that the Riemannian metric is given by this formula. It's a small perturbation of identity of order epsilon squared, and I have gradient v transpose gradient v. So as before, I had two-dimensional surface, so I had only one, essentially one curvature, which is the Gaussian or the scalar curvature. Here I have the full set of Riemann curvatures. And the Riemann curvature tensor of identity plus epsilon squared times something is given by this formula. So the leading order term in the expansion in epsilon is given by this operator C2, which basically is a bunch of second order partial derivatives. So when the dimension is 2, then C2 collapses to curl of A. That's why in honor of curl, I call it C2. So now I have to compute, right? I have to compute C2 not of arbitrary A, but of A which has a structure, which is given by this gradient V transpose gradient V. So I'm going to tell you what that is. So I have 4 indices, right? ij, st, because the Riemann curvature tensor has 4 indices. So if I have these indices ij, st, I'm going to look at the matrix of second order partial derivatives of V. I take the ij row, I take the st column. This gives me a 2 by 2 minor. And each element on this minor is a k-dimensional vector, because V was pointing to Rk. And I'm going to take something which is like the determinant of that, so namely a scalar product of the diagonal elements minus the scalar product of diagonal elements. And this is what I call this curly determinant Hessian V. So again, it has 4 indices, okay? So for every quadruple of indices, I have a scalar which is like basically the sum of the determinants of the ij, st, 2 by 2 minor. Of course, there's lots of symmetries here. And I sum over this codimension or coefficients in the codimension k. So I declare the following system of PDEs, the Monge-Ampere system. This curly determinant Hessian V, I equate it to the right-hand side. And the same as the Monge-Ampere equation reflected the prescription of the Gaussian curvature of shallow surface. Here, this reflects the prescription of Riemann curvature, full Riemann curvature tensor of a shallow manifold. Now, when d equals to 2 and k equals to 1, this becomes exactly the Monge-Ampere equation as we discussed on the previous slide. So when is this thing well posed? So the first necessary condition that's easy to observe is that, well, this determinant Hessian V is the C2 of something, is C2 of gradient V transpose gradient V. So I necessarily need that F is also in the image of C2. And one can check that a table F is in the image of C2 if and only if the 3 types of conditions hold, which are the leading, again, this is like collecting the leading order terms in the symmetries, algebraic and differential Bianchi identities. So if F does not satisfy this, then there is no solution. If F satisfies those conditions, then I can rewrite my Monge-Ampere system as F being in the image of C2, so F being C2 of some A, equal to, and this determinant Hessian V is, as I explained, C2 of gradient V transpose gradient V. So this means that gradient V transpose gradient V differs from A, from this prescribed A, by something that's in the kernel, by an element of the kernel of C2. So the next lemma is you can check that the kernel of C2 consists exactly of symmetric gradients. So I can write the weak formulation of MA as exactly what I've said, right? Gradient V transpose gradient V differs from A by a symmetric gradient of W. W is now a field from a d-dimensional domain into, again, Rd. So as in MA, I am looking for a V, which points from D dimensions to K dimensions. Here I'm looking for two fields. One is V from omega to RK, and the auxiliary displacement, if you want, W, which goes from D dimensions to D dimensions. So you can think about this V as of a Lagrange multiplier for this problem, which is whose weak formulation reduces exactly to VK. So I call it VK, I call it the von Karman system, because the left-hand side here arises in elasticity, describing the stretching of an elastic film due to the indeed out-of-plane scalar displacement. This is like in my first slide, dimension 2, codimension 1, and the in-plane displacement W. So these are the two systems that my talk will be concerned with. Now let me introduce another third system, which is very much related to those two. That's the system of isometric immersions. So in this system, we are given a Riemannian metric G. You can think it's a smooth map which to omega, which on omega d-dimensional set prescribes at each point a d by d symmetric positive definite matrix. And I'm looking for U such that gradient U transpose gradient U equals to G. Now U goes from this d-dimensional set to d plus k dimensional space. So now if G is a small perturbation of identity, and if I make an ansatz that my U is also a small perturbation of identity, where the displacement in the k, in that codimension direction, is denoted by V, and the displacements in the sort of in-plane d-dimensional set direction is called W, then writing gradient U transpose gradient U, it's quite easy calculation to see that the leading order term of the epsilon square is exactly what I've seen in the left-hand side of the system. So waiting A, let's describe G, and the leading order term here gives me exactly the von Karman system. Okay, so this leads to von Karman, which is the weak formulation of the Monge-Ampere system. So just to recapitulate, MA tells me, the satisfaction of MA tells me that the metric, which is of identity by the amount of epsilon square A, and the pullback of the Euclidean metric via the formation whose out-of-plane displacement is given by this V, coincide at the lowest order terms in the Riemann curvatures. And it turns out that this is perfectly equivalent to the fact that V can be matched by a higher order field W, so that now the metrics, not just the Riemann curvatures, but the metrics themselves coincide at their lowest order terms. That's the system VK, which, if you want, is like gathering the leading order terms in the II system under this ansatz. So this has all been an introduction of those three systems, three major players in my talk. And my talk is going to concern the existence and regularity of solutions to those three systems. Okay? And we will be concerned with a particular technique which allows for constructing solutions to different systems of PDEs, which is convex integration. So right away, let me quote a result that's a convex integration flexibility type of result for the system II. Okay? So it's for dimension D, arbitrary dimension D, and codimension K, just 1. It's due to Delellis and Szekelyhidi, published some years ago, and it goes as follows. So you take a metric, G, d-dimensional metric, and you take an immersion U0, okay, so it goes from d-dimensional set omega into Rd plus 1, codimension just 1, okay, and assume that it satisfies the shortness condition, that is gradient U0 transpose gradient U0 is negative definite with respect to G. So this is understood in the sense of matrix inequalities, should be valid at each point of omega. So I want to stress here that this condition is really, basically you don't need any geometrical connection between U0 and G. You can take any immersion U0 when you scale it by a very small, when you multiply by something small, and of course this is going to be negative definite with respect to G. So take an exponent alpha, this will be a regularity exponent, which is less than the minimum of those two numbers. So this beta is related to the regularity of the metric G. I don't want to be concerned with this exponent, but it also has to be less than this quotient, 1 over 1 plus 2d star. And that's an important regularity threshold. So what is d star? D star is the Janet dimension. This is exactly the dimension of the space of d by d symmetric matrices, right? If I have a d by d symmetric matrices, matrix, how many degrees of freedom do I have? As many as elements on top of the diagonal, which is d times d plus 1 over 2. So if you take any alpha less than, in particular, 1 over 1 plus 2d star, again, I want you to remember this regularity, this exponent, and hopefully I will explain why I need to have exactly 1 over 1 plus 2d star. So if you take any alpha less than that, then there exists a sequence of regularity C1 alpha, okay, immersions from omega to Rd plus 1, which converge uniformly to U0, that subsolution. And every member of that sequence is an exact solution. So not only I have existence of isometric immersions of my metric G, it's a d-dimensional metric in d plus 1 dimensional ambient space. But moreover, such immersions, such isometric immersions of regularity C1 alpha for any alpha less than that are dense in the set of all subsolutions. Okay, so that's a striking result. And here I just want to point out that the history of existence of solutions to the II problem, in a sense, you can split it into two directions. So one is the proofs that basically use like Nash-Moser implicit function theorem. So when the metric is smooth, then if the codimension is sufficiently high, then you have a smooth solution. In fact, when the dimension plus codimension equals to the number of equations, then already there exists a solution in the analytical class. An existence of solutions in C infinity is an open problem. And actually the same is true also for Holder regular solutions. On the other hand, for K, so this requires a large codimension, okay? But you can also have existence of those Helder regular, not C2, but C1 alpha solutions already at codimension K equal 1, okay? Not just existence, but density, as I explained in the statement of this result here. This goes back to the work of Nash and Kuiper and Borisov. And then finally, we had that very wonderful result, which is really the departing point for the results, my results and results of my collaborators that I want to explain. Yes.
So it really doesn't depend on how much that you're not going to be this selection may be much less than G.
Anything, exactly. It's exactly as I stated, right? You take your metric, you just need some room. You just need a wiggle. You need to be able to, you need to be away from G. Huh?
You could get
Sure, anything. Yeah. You need a subsolution. That's it. You need a subsolution. And then any subsolution, no matter what it is, you can think that G has a positive Gaussian curvature. So then you would expect from the isometric immersion to be convex, naturally. Oh no, take U0, which is a saddle. Take U0, which is a saddle. And then arbitrarily close to that U0, right? So of course, no convexity. Again, you will have exact solutions, albeit with regularity C1 alpha for alpha less than that. So that's one theorem I want to quote. Again, I stress arbitrary dimension, codimension 1. Now there is this older result due to Karman. Karman was a student of Hormander, who takes dimension D and codimension that's very large. So he says that if your codimension is sufficiently large, then the same result that I've seen here is true with regularity, any regularity up to C11. Okay, so let's read it. You take your metric, you set an exponent, any exponent less than 1. Again, that is here, so I have minimum between those two numbers. So this points to the regularity of the metric, but I don't want to be concerned about that now. Okay, so really the game, the discussion is about that exponent. So take any alpha which is less than 1. Then if you take k sufficiently large, then again, for any U0 that's a subsolution, you can assign a sequence of approximants in the C0 norm of regularity C1 alpha, that alpha, which you've chosen, and they are exact isometric immersions. So I want to stress that this result does not contain the Conti, Delellis, Szekelyhidi, Borisov, Nash, Kuiper approach at all. In fact, if you ask Karman if he can say anything for k which is 1, or actually even k which is less than 2 d star, he cannot say anything. So the proofs are given by different techniques. It's still convex integration, it's still Nash-Kuiper iteration scheme, but the result on the previous page uses the construction via so-called Kuiper corrugations, whereas this one uses so-called Nash spirals. Okay, so it's highly technical. And again, for k equal 1, we have this result with this regularity. For k which is sufficiently large, in particular, even in the small basic lemma, in the proof, you require k bigger than 2 d star, okay? And d star is like of the order d square. Then you can go all the way up to C11. So what happens in between? What happens for k which is 2 or 3? Bigger than 1, less than 2 d star, on less than d cube, which as in a global setting is what you need for the proof of this result. So here comes the first, my first result that I want to discuss today. So it's not for the system II, sorry, it's not for II, okay? It's for the von Karman system. It's for the von Karman system, which is the weak formulation of the Monge-Ampere system. Okay. So remember, what's the von Karman system? The weak formulation of MA is this gradient V transpose gradient V plus symmetry gradient W equals to the right-hand side. So take arbitrary V0 and W0 such that I have a subsolution to the same type of assumption as on the previous slide. So here, D and K, dimension D and codimension K are completely arbitrary, fixed. Take the regularity exponent alpha, which is less than 1 over 1 plus 2 d star over K. Then you can find a sequence of approximants of regularity C1 alpha, which are exact solutions. So observe that when K equals to 1, then I obtain exactly the same regularity exponent as in Conti, Delellis, Szekelyhidi. On the other hand, when K goes to infinity, this becomes 0, so I get to C11, which is consistent with Karman's result. And in fact, that also holds that if K is at least 2 d star, then you can get to C11. Okay, so here, you see when K is 2 d star, from this result, I get 1/2. But using this different technology, different approximation construction, I can actually prove that you can get to C11 already when K is fully static. So this is the first set of results in the progression of research in this context. So let me now show you the last result. Okay, the last result proves the full flexibility of the von Karman system in dimension 2 and codimension 2. Okay, so here if dimension is 2, then this star will be 3. Okay, so from this result, it follows that for K greater or equal than 6, I can get to C11. Or if K is, from this result, when K is 2 and this star is 3, then this would be, 1/7. But in fact, we were very happy to prove with my collaborator Delellis and Inauen earlier this year that for VK in dimension 2, codimension 2, we can get to C11 already. So it's a full flexibility of the Monge-Ampere system. Okay, so again, what's the result? The result is the same way as on previous slides. You take V0, W0, which are subsolutions, which is a subsolution, this pair, and then fix any exponent alpha less than 1. Then you have a sequence, the NWN, converging uniformly to V0, W0 of regularity C1 alpha, the fixed alpha, which are exact solutions. The particular corollary of that is that when you look at the Monge-Ampere system, okay, you remember VK was the weak formulation of NA. This Monge-Ampere system has basically no structure in dimension 2, codimension 2. Every C0 function is the uniform limit of some sequence of C1 alpha, any fixed, prefixed alpha less than 1 solutions of this. Okay, so you have a density of the C1 alpha solutions for a given right-hand side F, C1 alpha solutions of this Monge-Ampere system to the density in the set of all continuous functions. There's a full flexibility result, which is pretty striking. So my plan for the talk is to give you, try to motivate, give you a glimpse on what's the technique of proving this type of result. Before I do so, I want to present the history of the development, which started from Delellis and Szekelyhidi and ended up with this recent paper. So this is the development that happened over the past 15 years. So I present this history just for the dimension d equal to 2, but I will point out whenever a more general result was available. So what I've showed you a few slides ago, right, the Delellis and Szekelyhidi result, this concerns the II system of isometric immersions, arbitrary dimension, codimension just 1. So for d equal to 2, we can get with regularity C1 alpha up to alpha, which is less than 1/7. And this paper also showed the rigidity, established the rigidity, which is the lack of flexibility. I'm not going to discuss that for alpha, which is bigger than 2/3. Okay, so there is this gap. We have rigidity above 2/3 and flexibility below, at that point in the history, below 1/7. Then I had a result with Paxat for the Monge-Ampere equation. So this is just dimension 2, codimension 1. We basically used the deep understanding of this paper and we established flexibility with the same exponent, alpha less than 1/7. And we also checked that rigidity holds for alpha bigger than 2/3, the same as for the II system. Okay, so then the Delellis and Szekelyhidi, again for II, proved that in 2 dimensions, you can lower this exponent, you can up this exponent from 1/7 to 1/5. Okay, so like for any alpha less than 1/5, you have flexibility. And Kao and Szekelyhidi proved that the same is valid also for the Monge-Ampere equation. Again, just codimension 1. Then sort of I return to this type of problem, and I proved that for an arbitrary codimension, okay, dimension 2, but actually in that paper, I covered arbitrary dimension. But for dimension 2, the regularity for flexibility is any regularity below that exponent. So in particular, when k is 1, I get 1/7, which is like the original paper, original result here, okay, or here. And then in a subsequent paper, I was able to prove that arbitrary codimension, again, gives me just dimension 2, d equal 2, allows for flexibility up to 1/1 plus 4/k. When k is 1, then I achieve this 1/5 flexibility threshold, as in this paper. Okay. Then Kao, Hirsch, Inauen were able, by a very ingenious construction, to check that for the Monge-Ampere equations, again, k equal 1, they can improve 1/5 to 1/3. And then I was able to check that for actually now arbitrary codimension, you have just 4 possible situations. So when the codimension is 4, you can get to C11. When codimension is 1, then this is the 1/3, right? Like in that result. But codimension 2 and codimension 3, you have, okay, this is the regularity exponent. And then earlier this year, in January this year, we published on the archive the results with Inauen for the Monge-Ampere system, where in codimension k equals 3, we were able to achieve the flexibility regularity up to 1 minus 1/√5. Okay, so this is a very strange number. Basically, our construction involves progression of frequencies based on the Fibonacci numbers. That's why you have the √5. Now, I'm just quoting that result because this is the first time when this exponent, right, this number is larger than 1/2, even though we are using the Kuiper corrugations. So you remember a few slides ago, I showed you that using Kuiper corrugations, you have one type of results, and then there was this Cullen result, which used Nash spirals, and this allows you to get all the way up to C11. And it's not clear how to interpolate between the two results. So here, for the first time, we were able, using the Kuiper corrugations, we were able to get beyond the regularity exponent 1/2, which was the threshold in all the previous papers. You see this 1/3, 3/7, and 7/15, they are all less than 1/2. And then all the way, you jump all the way to 1 because you use this different construction. So here we use, for the first time, we use that first construction, and we were able to go beyond that exponent 1/2. In the meantime, Kao, Hirsch, and Inauen published a very nice paper, in which basically they obtained flexibility regularity threshold 1/3 for II system, which they had before for NA. Okay. And finally, with Dominique, we have a result which, for the MA system in 2 dimension, just obliterates all previous results, because we checked that in codimension 2 already, you can get all the way up to C11. Okay. And here is the result that's not yet written up. It's forthcoming work in which basically the same result that we have here, I am able to rewrite for the isometric immersion system. So it's a full flexibility, dimension 2, codimension 2. If you have any subsolution, then you can approximate it by exact solutions with any regularity C1 alpha, alpha less than 1. And this should be compared with the famous Pozniak's theorem, which says that you always have for a smooth metric, there always exists smooth two-dimensional metric, there exists a smooth isometric immersion into R4. Okay, there exists one single isometric immersion. So here I have a full set, dense set of isometric immersions, dense in the set of subsolutions with the same dimensionality, right? So these are isometric immersions into R4 of a two-dimensional metric, albeit with regularity C1 alpha. My plan now is to show you the major steps in the proof construction of the result, of this result, which holds for any dimension and any codimension. And then the regularity was 1 over 1 plus 2 d star over k. This was the first theorem which I proposed a few slides ago. So how do we prove this kind of results? So the construction has 3 parts. We have steps, we have stages, and we have iteration of non-stages, which is the Nash-Kuiper algorithm. So a stage type of result goes as follows. Okay, so let's read it together. So I have V and W, and now I compare the given right-hand side A with this von Karman content, gradient V transpose gradient V plus symmetric gradient W. If you remember my VK system, which is the weak formulation of the MA system, is basically equating this table with the given A. So I declare the difference between them as the defect. This defect is non-zero. And now you have your V and you have your W. I'm going to construct V tilde W tilde, which is close to the Karman contents corresponding to the V tilde and W tilde is smaller than D. And then I will have a cascade, I will have a progression of iteration of this construction, and hopefully I will get D to 0. So the theorem says that it is possible to construct V tilde and W tilde, okay, such that the new defect, right, this defect, is basically the old defect divided by a large number. So fix sigma, that will be a frequency, and you can decrease the defect by sigma to some power s. Now, what this s is will be the crucial part of the construction. Okay, so I'm not telling you what s is. For different problems, different dimensionalities, different d and different k, there's like a different s. But we want to prove a theorem of this type. Now, the price to pay is that, well, V tilde is close to V in the C1 norm by the square root of the defect. So if defect is small, then I'm staying close to V. V tilde is close to V. The same is true for W tilde. However, the second derivative goes up. This M is like the second derivative of V by sigma to another power j. Okay, so again, what is the stage theorem? The stage theorem is a type of construction which tells you that, oh, if you have V and W and there is an associated defect, which, okay, here is assumed to be small, less than 1, then you can modify your V and W to V tilde W tilde so that the defect goes down by sigma to power s. However, the second derivative goes up by sigma to power j. Let me now show you how having a stage type theorem like this implies that you can get flexibility with regularity exponent alpha less than 1 over 1 plus 2 J over S. You remember I showed you a series of flexibility theorems. There is always the question, what is this alpha? So in Conti Delellis and Szekelyhidi, I have alpha was less than 1 over 1 plus 2 d star. In my theorem for VK, I had alpha less than 1 over 1 plus 2 d star over K. Many other results of this type. Okay? So this is the crucial point I want to explain to you, how this 1 over 1 plus 2 something arises from the quotient, from the ratio of the blow-up rate of the second derivative versus the decrease rate of the defect. Okay? And then, of course, if I want this to be big, then I want J over S to be small. So I will want to decrease the defect fast at the least possible expense of the blow up of the second derivative. Now, how to do it is another question. Okay? This is the first ingredient of the proofs. So I iterate this construction. I set V0 and W0 to be my given V and W. And then I iterate the stage. So you remember the second derivative blows up like sigma to power j. So if I iterate it n times, then the second derivatives are like sigma to power j times n. On the other hand, the first derivative, right, the first derivatives are like square root of the defect. But the defect goes down like sigma to power s. So the first derivatives go like, okay, the previous defect to power 1/2, but the previous defect is sigma to power s times n minus 1. I iterated n minus 1 times up to get to the previous position, and now I have the square root. So I have the bound on the second derivative, and I have a control of the first derivative. And now I interpolate. C0 alpha norm interpolates between C1 norm to power alpha and C0 norm to power 1 minus alpha. So I get that the difference of the gradient Vn and gradient Vn minus 1 in C0 alpha norm is like sigma to that power. So for the sequence to be Cauchy, okay, for the sequence Vn to be Cauchy in C1 alpha, I need that this exponent is less than 0, it's negative, which is equivalent to alpha being less than that. That's all. That's the proof. So how do I? Okay, so this was just to explain how the stage type theorem gives you the final result. So how do I prove the stage theorem? So I look at the defect, which is A minus my von Karman content. And I want to rely on the one-dimensional type constructions. So this is a positive definite, so X's defect is a positive definite, is a field of positive definite matrices, symmetric matrices. So it turns out you can decompose each matrix like that into D star rank 1 matrices. Okay, so the space of symmetric D by D matrices has dimension D star. And it turns out that you can take the basis of that space as the rank 1 matrices of the form actually eta I tensor eta I, where eta I is some unit vector in Rd. So this is what I do. I take my defect, I decompose it into rank 1, like linear combination of rank 1 matrices like this. And then there is a way, a procedure called the step, we'll see it on the next slide, which allows you to modify your V and W to V tilde W tilde, so that the difference of the corresponding von Karman content is exactly one term of this form. Okay, so here, because of positive definiteness, basically the coefficients here will be positive, so I can write them as a square of something. Okay, so again, I will have the defect. I write it as a linear combination of rank 1 defects, and I will have a cascade of highly oscillatory modifications of V and W, those will be called V tilde W tilde, so that the outcome is that I am able to annihilate one of the terms in that decomposition. So then I do annihilate the next term and the next term and the next term. After this star of steps of this type, I hopefully get the theorem, which is the stage theorem. And then by Nash-Kuiper iteration, I get the final result. So how to do this? Okay. So you have your V, you have your W, and say you want to annihilate, you want to decrease your defect by an element of this form. Okay, just a square eta tensor eta. Eta is just an in-plane unit vector. So what you have to do, you have to add to V. Now W has a more complex construction, but let's focus on V. You have to add to V. So this gamma is like a bunch of sines and cosines, and highly oscillatory function, which oscillates in the direction which is aligned with this eta which is here. The amplitude is A. A is the square root of this magnitude of this rank 1 defect that you want to annihilate. And you oscillate with frequency lambda. Lambda is just anything, okay? Just large frequency. And this E is one of the codimension vectors. Okay, so you add to your V just a one-dimensional in the codimension space oscillation, and the oscillation takes place in the along a single dimension, which is corresponding to that rank 1 matrix in the decomposition of the defect. Okay? So this lemma, which is this calculation, shows that indeed then the new von Karman content minus the old von Karman content is this a square eta tensor eta, and you have a bunch of error terms which are of the order 1 over lambda. Lambda is a large number, it's a large frequency, okay? So of course, when lambda is large, then this is small. So you are replacing this O of 1 large, however, rank 1 portion of the defect by a much smaller defect of the order 1 over lambda. And lambda is large, but that's very small. So all those three terms here are, pose certain difficulties in the proof. But let me now concentrate on the first term. So what's the form of this error term? It is 1 over lambda. Okay, I have this A, the same A that I have here. This gamma, again, you should think that gamma is just sine or cosine, a periodic function. And then I have the second derivative of V. V is my out-of-plane displacement on which I am building my modification V tilde, whose defect is much smaller than the original defect. Okay. So let's do this, and let's see what kind of new defect I obtain and how far is V tilde from V in the C1 norm and C2 norm. Okay, I'm trying to prove the stage type theorem. So first of all, this A, so the defect D is decomposed into A square eta tensor eta. So A square is like a linear projection. So A square is like D. So the C1 difference, C1 norm of V tilde and V, right? So the difference is just this term here. So the C0 norm is like 1 over lambda. The gradient, you remember this is oscillatory, so when you take the derivative, lambda comes out and cancels this 1 over lambda. So what's the magnitude of the gradient of this? This is like A. And A is like the square root of D, and that's what's written here. On the other hand, the second derivative, if I differentiate again, then I have another lambda coming out here, right? So the second order difference is like lambda times A, and A is the square root of D. So now in the new defect, right, in D tilde, in the new defect, I have gotten rid of the first principal rank 1 defect in this decomposition. So here I have the sum from I equal 2 to D star, okay? And the price to pay for this is this error, which is of the order just discussed, right? So this is 1 over lambda, and A is like square root of D, and now I have the Hessian. So let's now continue the second sense. We want to from now until lambda. Then the second term here. Very well. So now the D double tilde will be the sum of rank 1 terms starting from I equal to 3 to D star, right? I've annihilated the first one, and in the second step, I annihilated the second one. And this is the error that I'm carrying over from my first step. And now the new error is again D 1/2 divided by the frequency. It doesn't have to be the same frequency. I can do it with any frequency I want. But now here, you see, I have the second derivative, not of V, but of V tilde, because I'm building my second step on the first step that is on V tilde. And the second derivative of V tilde is like already like lambda. So to have those two terms at the same order, I need lambda 2 to be at least like lambda squared, because this guy is like my second derivative here, but times lambda. So I need lambda 2 to be like lambda squared. But this means that the second derivatives of V tilde are like now this lambda 2, which is lambda squared. So now after applying it D star times, yes, I have removed all the first order terms in my defect. So the new defect is like the old defect divided by lambda, right? Just the terms like this. All of them are of order 1 over lambda, right? I have no terms of order 1. However, the second derivative went up by the power of D star, because I have D star steps, and in each step I have to increase the second derivative by the order of lambda. So that's exactly what we've seen in the Delellis and Szekelyhidi result, where the increase of second derivative is like lambda to D star, and the decrease of the error is like lambda. So your J over S is D star. So the exponent is 1 over 1 plus 2 this, which is D star. Okay, that's it. So now I don't have much time left, but let me try to explain what happens if I have more than one codimension at hand. So now I can define my V tilde and W tilde not just by sending one single perturbation, one single codimension, but I can use K codimensions at once. And I can, in one step, cancel K principal defects of the rank 1 type here. Okay. So now my V tilde and W tilde in the von Karman content will differ from V and W by K principal rank 1 defects, and then I have higher order terms. So the plan is to cancel K primitive defects all at once by using K codimensions. And when K is even larger than D star, you can cancel all, after canceling all first order primitive defects, you can proceed to canceling second order defects obtained as primitive decompositions of the error between original and the decreased defect. And then you can cancel even higher order defects, adding K tuples of single codimension perturbations for a total of least common multiple of K and D star steps. So basically that's what you do. You declare your capital N to be least common multiple of D star and K. So this is some capital J times K and S times D star. And you have to alter your frequencies. So whenever you pass by a multiple of K, your second derivative goes up by 1 power of the frequency. And then you have to alter your frequency after the K tuple of primitive defects have been removed by sigma, exactly the same as I explained here. This lambda 2 had to be lambda squared. So you had to multiply because here you have just one codimension, and now you are building your new V on top of the previous V. So your frequency goes up by 1 power. So the same here, after you've exhausted all K codimension directions, your frequency will go up by 1 count. On the other hand, whenever you pass a multiple of D star, this means that you've canceled all the primitive defects in the decomposition of your defect at hand, and there is D star of them. So whenever you pass a multiple of D star, then your defect goes down by 1 extra power of sigma. Okay, so you have this construction, and at the end of the day, your second derivative goes up by the number of times that you pass over a multiple of K, your codimension. That was called J, right? You remember I told you the least common multiple of D star and K was, okay, J times K, which is S times D star. So your second derivative goes up each time you pass over full set of codimensions, K. So sigma to power J at the end of the day. On the other hand, each time, so what happens with the defect? Defect goes down by sigma to power S, which is the number of times that you pass over a multiple of the star. And what is J over S? Well, it's J over S because N was the is common multiple of K and star. In fact, J over S equals to D star. Okay. And this gives you the regularity exponent 1 over 1 plus 2 J over S, which here we have observed when we take the star. Okay, this is the essence of the proof. And I just 1 remaining minute. I won't have time to discuss this at all, but I just want to point out that that's actually my original source of interest in this kind of problems, which now we have run by themselves. And it's the so-called quantitative isometric immersion of thin films. So this is related to the elasticity of pre-stressed materials, where we have the energy. It basically checks how much of the formation is or is not an isometric immersion of a given metric on your referential configuration. So this is a thin film, the Cartesian product, the dimensional domain, and a small thickness interval of length to h. H is a small number. And then turns out that the scaling of the infimum of the energy is related to the magnitude of the Riemann curvatures of G, and in particular, the infimum of the energy can be computed using the regularity. I mean, I don't have time, sorry. Can be computed using the optimal regularity of the isometric immersion that I can read from this type of Convex integration constructions that I discussed. So this is just a picture, just showing that there's actually many experimental setups with which you can embed a metric, a pre-strain metric, a thin film, and then when you activate the metric, you are getting all curious shapes of thin films, which are linked to the minimizers or approximate minimizers of type functions like this. We can work extensively in this direction, and we actually book a couple of weeks ago about this type of supervision problems. It's a good one. So,
So, are there questions?
Thank you, Martha, for a beautiful seminar. I wanted to ask, so it seemed that in your stage theorem, the arguments seem quite quantitative in nature and getting this Cauchy sequence to construct the C1 alpha candidate here. Do you have any hope of getting a rate of convergence for your main results when you construct UNs converging uniformly to the subsolution U naught? Yeah, so can you quantify the rate of convergence of UNs to U naught? So your main theorem is that there exists, a collection of UNs, which are exact solutions, which converge uniformly to the subsolution.
Prescribe the threshold epsilon, and from within the threshold epsilon, find the exact solution.
Yeah.
So the question here, I'm just trying to understand the question here. Okay, then you fix your epsilon. What is the blowout? Okay, for epsilon, how is that? So, right, that's what we want.
I want to measure the distance between UN minus U0. So like as a function of that. The UN converges to U0 uniformly.
Yeah.
So my question is, from this construction, do we see what is, the rate of convergence of UN to U0?
No, I think the right question, no, so just, I don't have what it's at, right? So I have, so fix your, it's any rate of conversion. The question, when the question would be, the right question would be, how UN goes to U0, what is the rate? Because I'm, okay, right, one over n. And then I'm UN. Zero is one over n. I can do whatever I want.
Okay.
Anything I want for any epsilon.
I see.
Okay. I think the question you can go around the property of the end and I can epsilon from the zero.
Yeah.
Okay. So of course I know the C0 distance is that epsilon and 1 over n, whatever you want, but what happens with the C1 now, what happens with the C2?
Yeah. Right. Okay. Thank you.
Other question?
This sort of, all this convection, they're all striking. But it would say, two things. One, that there are a lot of solutions, because whatever the equation is. So you could say, well, okay, the uniform convergence, but it has to do with derivatives, it's not happening to anything. So it's not, so I'm surprised that with oscillations, you get, you get there. So what would be, so what's the sort of takeaway from these results?
It's way that the curvature is not defined because it's just one alpha. You cannot do it with C2.
Exactly.
Why you cannot do it with C2? Because you have a G. So you can prove that, for example, in codimension, you have a positive, when you connect it with positive Gaussian curvature, then C2 solution, C2 is immersion, automatically is locally convex. Okay? Now you can tweak the proof, your favorite, I didn't talk about that before, okay? Take your favorite proof of that result, and then you can show that if it's going to be the same, even if you don't take C2, but you take C1 alpha with alpha sufficiently close to 2. It is actually close to 1, right? Yeah, so C2, you are going to get the same. In fact, what I'm saying is true and unbelievable difference. Okay, there's a proof that you are checker. Why? Because, if you take something C1 alpha, which is close to C2, you can say, oh, I modify it, and I have a sequence of approximant whose second derivative blows up of certain rate. So if this blow up rate is sufficiently small, exactly the same, which we're responsible. And in that kind of turns out alpha bigger than 2/3 is enough for that. Okay, let's have a couple of lines proof which works here. It is the same point of view that's used in the fluid dynamics. Exactly, so we have all that questions, and then the question is, oh, we have a solution, is the energy conserved? Okay, so when the solution is sufficiently regular, then the trilinear term in the proof is 0. Now, if it's not regular, then this will modify, and you have the trilinear term, you have a commutator estimate, which tells you that you have, something that the blowout rate of something expansion below, so that you can see it out. Okay. So I guess what I'm saying is that what's in the fluid dynamics, what's the energy conservation property, here is existence of curvature. So for C1 alpha, below alpha, now place that out in combination 1, alpha less than 1/3, you let you come here. The question is, what's the threshold? What's the threshold of alpha? With some weak notion of curvature can be defined, and you would extend beyond the threshold, and above the threshold. But it's not like in other equations, but we do have component of vector, and it's resolved with threshold of 1/3. And here, there's no doubt. Because it's 1, in 1/3 and 2/3. The interesting is, because you mentioned proof, there's no doubt, there's no rigidity at all. Okay, because by that. In codimension 4, we have the full flexibility of the non-Euclidean. So any alpha up to C11, you get the flexibility. The conceptualizing that the curvatures as a selection principle for the same manner as the fluid dynamics. The conservation of the kinetic energy being set as a selection principle for the activity. But here for gradient V transpose gradient V equals to G, of course, for C1 alpha it's well defined, for C1 it's well defined. We have additional curvature type constraint, which is not really as visible as pronounced here as it is in the problem.
Thanks.
Yeah. If not, then the speaker, and we can complete.